Okay, so I know it's early in the morning, and I hope this chapter isn't too hard. We only have one section to cover today, 18.5. So hopefully it's not too stressful in the morning. So this one is about a step in a chemical reaction called the rate determining step. So in most reactions, even really simple ones, as you have already found out now, like in the enthalpy change reactions, the Born-Haber cycles, that most reactions have a lot of smaller steps in between them. If it isn't just the ions dissociating, then it could be like intermediate steps that the catalyst does. So I'll show you an example later, but even something like this, like, well, my usual example of A plus B reacts into C. This might be the overall reaction, but there could be intermediate steps like this. So first A and B dissociates into something like D and E. And then this has another intermediate step. A and D reacts to form F and E. And then finally, F and E reacts into C. So the overall reaction is this, but these two intermediate steps do exist. So this reacts into F and E. So they do exist, and without them, the reaction couldn't take place. So all these steps, when put together, is called the reaction mechanism. It's the mechanism of how each molecule actually reacts. And this equation just gives you the overall reaction. So usually those intermediate stages are very short-lived. So when they react, they come into existence and then they react back very quickly. So that in reality, the intermediate steps don't have any real effect on the physical properties of the reaction. They're only there for like milliseconds or even shorter. They're only there because it's energetically more favorable to react in that way instead of reacting directly. But a catalyst usually, how a catalyst works is that it usually creates an extra intermediate step that makes it much easier for the whole thing to react. It's a bit like if I'm standing on the ground and I want to get, there's this really tall building and I want to get here. Of course, I can just jump really high or I can climb the wall, but it's easier if somebody put a step here for me so that I can go on the step first. And then after I go on the step, I can go on the higher thing. So the intermediate stages are a bit like these smaller steps for the reaction to step on before they get onto the higher or the last stage. And a catalyst helps even more by maybe adding another step. So it's even easier for the reaction to get here. So these intermediates are so short-lived, it is usually difficult or impossible to identify them or to even know how fast or the properties of these reactions. So today we're going to look at what's called the rate determining step. So that's the step that determines the rate of reaction. And using that, we can look at which intermediate is slow, which intermediate is fast. We get to know a little bit more about the intermediate stages. It's really difficult to know about the intermediate stages just by experiment because they're so short-lived. So usually it's determined by extrapolation from the Born-Haber cycles. So the rate determining step, it means that it's the step, the intermediate stage, that determines the rate of reaction of the whole reaction. So when there are multiple steps, the steps usually have an order, meaning that, well, if it's like the one before, like A plus B becomes C, I might have maybe 3 intermediate steps. A plus B, B dissociates into D and E, and then A and D react to form F and E, or something like this. And then maybe I have one more. F and E react first into X and Y, but these two become this. So this is just an example. If I have these intermediate stages, they happen in an order, meaning that first it's number one, and then number two, and then number three. It's not 3, 2, 1. It has to happen in this order. So what does that mean for us? So it means that if one of the steps is slow, then that step determines the rate of reaction of the entire process. It's a bit like, have you guys ever watched the TV show The Weakest Link?
No, the what?
The Weakest Link.
Oh, no.
It's like a game show where teams of people, they have some challenges, they have to do some things, they have to answer questions. And there's always one person who is the weakest link, meaning that they are like the slowest or not very good at it. And usually the whole team's performance depends on that one. So I think there's a metaphor, an idiom for it in English. It's it's the weakest link. So if you have a group of people, no matter how good everybody is, the strength of the team is only as good as the weakest link. I think that's the idiom. Maybe a way to imagine this is if I'm playing tug of war. So I'm trying to pull this rope, and there are people who are holding on to each other like this, and they're holding on to each other. So if they're pulling, even though person A, B, C, even though they're all very strong, if person B is very weak, then the whole team's performance is limited by person B. Because as soon as you pull too hard, person B will fall down or he'll let go. So the same thing with these steps. If I have step one, so step one, and then step two, and then step three, if all of these are happening very fast, but step two here is the slowest, then the whole reaction is slowed down just because of step two. Like, this kind of makes sense, right? It's like there's a queue and step one is happening very, very fast. It's done with its work. And step two now is happening, but it's so slow that even though step three happens fast, it needs to wait for step two to be finished before it can start reacting. So the whole process, the whole reaction is determined by the slowest step in the reaction. The same way, like if I'm playing tug of war, the whole performance of the team is determined by the weakest person in the team, not the strongest. Especially if you're playing a game of tug of war. Even though A is maybe Superman, the limit of the strength of the team, the limit of the team is the weakest one. Same thing with this one. Even though step one and step three happen at the speed of light, if step two happens slowly, then the whole reaction is slow because step three cannot happen until step two is finished.
Oh, okay. Makes sense. Yeah, makes sense.
Yeah, it makes sense, right? Does that make sense for everybody else?
Yeah.
Yes.
Yeah,
Yes.
okay. Where is Zach?
I have no idea.
No idea.
Oh, okay. So the slowest step, that's the rate determining step because it determines the whole rate of reaction. It's the rate determining step. Or another word, it's also called the rate limiting step because it limits the rate. Okay, so any step that occurs after the rate does not affect the rate. Why? Because before 1, 2, 3, if only step 2 is really slow, that once this is finished, step 3 can just finish the rest of the tasks really quickly. So if I have more steps. So step 1 happens really fast. Step 2 is here. There's a queue. Everybody's waiting for step 2 to finish. But once it's done, step 3 and 4 are so fast that once step 2 is done, they can just finish the rest of the reaction. So all the steps that are after the rate determining step does not affect the rate. So step 3 and 4. That's because once it's done, they can just carry on. So usually, species, so the reactants in step 3 and 4, so whatever is after the rate determining step, it does not appear in the rate expressions because it does not affect the rate. But these steps that happen before the rate determining step do affect the rate. So if 2 is already slow, it's even worse if both 1 and 2 are slow. So not only does the whole reaction have to wait for number 2, it also has to wait for number 1 before number 2 can happen. So whatever is before affects the rate, but whatever is after, it does not affect the rate. So I think now we can look at maybe an example. So my amazing example of A plus B plus C again. So for example, I have this. This is the overall reaction. So my first intermediate step is that A and B react to form D first. So then I get D plus C, right? But then D dissociates into E. So in my first step here, if I have a test tube or a beaker with A, B, and C, so when this reacts, it becomes X and Y. First, A and B reacts to form D. So it forms D. And then in my second step, D dissociates into E. Well, not dissociates, it transforms into E. It's going to be E. And then in my in my third step, finally E and C react to form X plus Y. So these two react, these two things, they react, and they form X and Y. So finally, I get to my final product, which is X and Y. So I have 3 steps in this process. And I can't, you can see how it has to be in this order. I cannot have 2 before I have 1, because 1, I don't even have D yet. So I need to have D first before 2 can happen. And step 3 can't happen before 1 and 2, because then I don't have E. So if I'm just going to make up the rate. So if step 1 is quite fast, step 2 is slow, and step 3 is also fast, then step 2 is the rate determining step. Before number 3 can happen, it has to wait for this to happen, because otherwise it doesn't have E. So in this instance, step 3, it does not affect the rate, because it's after step 2, after the rate determining step. But step 1 does affect the rate. So if I have the rate expression, then it's only the species. So I'm going to erase my drawings. It's only the species in the steps that determine the rate. So step 1 determines the rate, and step 2 determines the rate. So the species that are reacting in these 2 steps are A, here, B, and D. That's why in this reaction, C it doesn't affect the rate expression because C doesn't react until step 3. And using this, we can also figure out why in some reactions, not all of the species have an effect on the rate expression. So you might ask yourself before when you're doing the rate expressions, why is it only sometimes, even though it has 3 species like this, it's only A and B? Well, now you know the answer because C happens in a step after the rate determining step.
That's why I got answers wrong.
Which one?
For 18.5.
Did you do the summary questions for 18.5?
Yeah, I did. I sent it to your WhatsApp because I can submit. Yeah.
Yeah, so I realized later on that 18.5 we haven't discussed yet, so it's now. So that's why I didn't make it available yet for you to submit.
Oh.
Yeah, I thought you were talking
And can
about
I do it again later?
Yeah, sure, of course. Yeah, sorry about that. I thought you were submitting 18.4.
I was submitting 18.5.
Yeah. So obviously you cannot because I made it. I gave it a time frame for you to do it, so it wasn't that day yet.
I had a quick read for 18.5, but don't really understand. So yeah.
Okay. So hopefully after this lesson you'll understand it a bit more. Okay. So now we're going to look at a real example. So not just ABC, I'm going to have a real reaction. So we have propanone. So you guys from organic chemistry should kind of remember what it looks like, but it's okay. It's not important to know exactly what it looks like. It's reacting with iodine, and there's going to be the propanone is going to give this molecule its hydrogen, and one of the iodine atoms is going to attach to the propanone and form iodopropane. So this reaction is pretty common, and it's also pretty simple. And if you remember from the organic chemistry thing, there's a lot of curly arrows. There's quite a complicated reaction mechanism, and that mechanism involves multiple steps. So even though the overall reaction is just one step, in the reaction itself there are multiple steps. Like first, the bond of the hydrogen is going to break, and then there's an electron exchange, and then one of them is going to be attracted, and then one of them is going to be an atom donator, a proton donator, and then finally you get to the last stage. There's a couple of steps, and those are what are called the intermediate steps of this reaction. But which one is the rate determining step? So in this case, the catalyst is a hydrogen plus, so it's a proton. And just to tell you, the rate expression is propanone and the catalyst. So the iodine here doesn't even make any effect on the rate. And neither do the products. So why does the iodine not appear in the rate expression? So let's have a look at all the steps. So these are the steps. So this is propanone, this one, and this is the catalyst. So first, without looking too much into it, first something's happening to the double bond here. The double bond breaks, and the oxygen binds with the hydrogen, and this becomes a plus ion because the electron is transferred to the carbon. And then once that happens, something's happening with this carbon. There's a double bond, and it loses the hydrogen. So essentially, there are lots of steps. You don't have to look at it in too much detail. But iodine doesn't come into play until the third step. And it's only in the third step that iodine starts reacting. So this is the third step. So if you pay attention to the fast, slow, slow, fast and stuff, the slowest reaction is the first one. So that means, if you remember, all these steps after the slow reaction don't affect the rate of expression at all. So none of these species, this one, this one, this one, this one, none of these species affect the rate of expression. They don't affect the rate of reaction. The only species that affect the rate of reaction is propanone and H plus, because it's in the rate determining step. And since it's the first one, the first step, there is nothing before this step. So that's the only two reactions, the only two species that affect the rate expression. Does that kind of make sense?
Yes.
Yeah.
Yes.
Makes sense.
Okay, that's good. So by way of, if I know the rate of expression, I know what it looks like. And now the question is reversed. Using the rate expression, how can I know which step is the rate determining step? So my example of ABC again. Let's say, for example, I have these intermediate steps, but I don't know which one is slow. I don't know which one is fast. I don't know which one is the rate determining step. But I do know that the rate expression is only first order. So maybe I know the value of K, and by the units of K, I can find out that the rate expression is only first order, meaning that there's only one species that affect the rate. Only one species. So using this information, I can do some detective work and find out which is the rate determining step. So it can't be this one, because in this reaction alone, there are already 3 species. So there's no way. It can't be this one. It also can't be the second one, because even though there's only one species reacting here, if it's this one, then the step before it also should affect the rate. So if it was the second step, then the rate would be rate equals K, A, and B. So if it was the second step, then it would be like this. So it would be second order, because now I have 2 species. So it must be the first one, because I only need one first order. So the only species that affects the rate is A, and since there are no steps before it, then that's the only one. But if it just so happens that my rate expression is second order, then I know it has to be the second step. That's the rate determining step, because then I have both A and B in the rate expression. And if the order is 5, then it's the third one, because then it's A, B, C, D, E, all of these.
Right.
So using the rate expression, you can work backwards and also figure out which one is the rate determining step. So this is useful because if you're devising an experiment and you're realizing your experiment takes much too long, it's too slow, it takes ages before anything happens, then I can find out which is the rate determining step. So for example, if it's this one, this is the rate determining step. So this is the slow one. I can increase the concentration of only B so that my reaction is happening faster. Oh, Zach is here. So if I'm trying to do this reaction and it's taking forever, I can, of course, increase the concentration of all my species, A, B, C, D, E, everything. But then that's so wasteful. It's so inefficient. If I know which one is the rate determining step, I just need to increase the concentration of the species in that step. So increasing the concentration of E doesn't even do anything to the rate. Increasing the concentration of C doesn't even do anything. So I just need to increase the rate, the concentration of P, if this is the rate determining step, so that it's faster. Okay, hi Zach, are you okay?
Yes. Okay, miss.
What happened?
They summoned me to some meeting. It's about some like neighborhood stuff.
about some
Oh.
complaints.
What? Okay, that's
Again.
Yes, Riz.
Mantap.
so early in the morning as well.
Yeah. Yeah, apparently they said they came last night, but it was so late. We were all asleep. And so they came again like 8:15 or something.
Why did they come to you? Are you the is your dad or you the RP person?
Uh, well, I filed a report, but they want to speak to my dad about it. I don't know.
I see. Okay. Well, that's okay. So this is actually the last thing, the last slide that I have. Oh yes. So one last thing. If sometimes in the rate you have something like rate is k a square, that in terms of the steps, in terms of the
Second
steps,
step.
it just means that a happens in, so well, in this example, it's not. But if, for example, in the rate determining step, a shows up again, then a is somehow there twice. So it's just a square. So let me come up with a better example. So if I have a turns into d, and then this one, a plus b equals d, like this. So say, for example, the second step is the rate determining step. So then a is there twice. So that means it's a squared. But in this case, you also have b. So when you have square, it just means that in your calculation or in figuring out what the rate expression looks like, a was in both the rate determining step and the step before it as well. So a was there twice. Okay, so that's actually the end of my slides. So do you guys have any questions?
Yes.
Yeah.
Can I ask, how can you tell which species is the catalyst in a reaction?
So usually the catalyst, the definition of a catalyst is that once it reacts, you get it back without it changing. So in a reaction like this, none of them are catalysts because none of them are preserved after the reaction. So if I have something like this, let me do it, like A plus B plus C, and then I get X plus Y plus B. So this means that B, even though it reacted, it
B
didn't change.
is the
So that means
catalyst.
it's B.
Okay.
Yeah, but be careful. Maybe B isn't even reacting. But a catalyst is by definition, it doesn't change when it reacts. So normally it's not even in the, it's not written in the equation. It's on the side, like, oh, on the side, H plus.
Yes, yes.
Okay.
Guys,
So
can we just discuss the summary questions?
the summary questions. So the,
Yeah.
okay, sure. How come?
I don't think I still get the right answer. Right?
Okay, sure. So, but if you guys can have it open on your computer, so you guys can have a look at it, not just on my screen. So let me head over to the summary.
Yeah, I have my book right now.
Oh yeah, that's good. Great. I don't have the book, so I'm going to have to find the questions first.
Want me to take the picture?
No, it's okay. So the teachers, I'm not sure if you got it, but the teachers got ebooks.
Yeah, we got ebooks as well.
Okay. So I just need to open the ebook. Just give me a second while it loads. Oh, I should stop recording.